Now we have applied Faraday's law in our first example in an analysis of a circuit where we're first beginning to look at Faraday law effects inside of circuits. And what this circuit featured was some spatially constant magnetic field. It actually exists everywhere throughout all of space. And what we do is we imagine we have this, it's spatially constant, but it's varying in time. And in particular, it was increasing in time. And then to harness this field using a circuit, what we did is we made a series of loops or a solenoid such that the field was going through the solenoid, and then we connected that solenoid to some external circuit containing a resistance R. And then we began to analyze how this circuit would respond to the presence of this changing magnetic field. We began again very fundamentally with Faraday's law. All we did was rewrite it with the minus sign on the other side of the equation. When we do things like that, it becomes very useful because now we can reformulate this in terms of Kirchhoff's second law. Kirchhoff's second law used to say that the sum of the voltages around a loop, which is nothing other than this minus closed line integral of E dot dl, it used to say that that equaled 0. But now we see when we're in a not a steady state situation where there is some time variation, it actually equals the time derivative of the magnetic flux captured by that loop around which we're computing the voltages. We then carried out an example calculation using our circuit, and if we were to go around our circuit in the direction that I've indicated to you here, clockwise, and what we did was we presumed that the direction of the flow of the current I would be as follows. And again, if we're wrong in that presumption and it flows the other direction, of course, we would expect then the current to come out with a negative sign. Once we've set ourselves, though, on this presumed direction of current, immediately then, from Kirchhoff's first law, we know that current flows all the way around our circuit, and we see then that the resistor has an upstream side here and a downstream side there, so that the current flows from upstream side to downstream side. And then minding our sign conventions, as we go across this resistor, going through our Kirchhoff's loop, we pick up a voltage drop of IR. The next circuit element we hit is this inductor, and we just travel directly through the conducting parts of this conductor. And we imagine it actually to be an ideal conductor in which, because the conductor is stationary, there can be no electric fields. Consequently, there is no potential drop as we go through the inductor. But what all of this has to equal now is an additional term coming from the changing magnetic flux. We calculated that flux, and I've indicated its value to you in here. What there are basically in that calculation are we have n turns, right? This area A has magnetic field passing through it n different times, capital N, once for each turn. Each turn has an area A. And then we can multiply that by the flux of the magnetic field through each of the turns. To calculate those, of course, we break out the dot product. We have our factor of n from before, of course. The magnitude of b we write down, and that comes out of our integral. We're then left with the integral of the magnitude of dA across each of these faces, which then, of course, just gives us the total area A. The final factor we have left to decide is the cosine factor. Now, if we think carefully about our example here, the direction around which we are threading this loop is such that we're going around this way. So as we come into the inductor, we come across to the right in front and to the left and back, and then coming back down around, it's going to be again to the right in front and to the left and back, and then looping back around, right in front and left and back. Now, to carry out that dot product, I need to know the direction not only of B, as I've indicated, but also the direction of dA. Now, using our right-hand rule, if we look at this area and we curl our fingers, right-hand rule 2, around in the same direction as this loop goes around that surface A, we see that our thumb then on our right hand naturally points upward. So dA is perpendicular to that area, and more critically, it's in the upward direction. So we see then that the area normal, dA, and the magnetic field in this case are in exactly the same direction. So our cosine becomes a cosine of 0 degrees, not 180, and the cosine of 0 is a plus 1. So the sign, very carefully worked out in this case, is positive. Next, what we did is, after understanding the basic structure of the equations governing this circuit, we actually solved for the current. And when we do that, we noticed very nicely that the current comes out actually with a negative sign if the magnetic field, as we stated in the problem, is increasing with time. That simply means that the current actually has to flow here in the opposite direction. And we can see that. That is completely consistent with Lenz's law. After all, Lenz's law tells us this induced current has to be such that it tends to decrease the flux through the loop. It has to oppose this increasing magnetic field. But if the current actually flowed in the indicated direction, notice that if the current were to flow this way, again, by the second right-hand rule, the magnetic field that this current itself would induce would also be in the upward direction. In particular, it would have our standard form of the field of an inductor inside of itself, which is mu naught times the winding density N times the total current I. And if we were to add that induced self field from the circuit onto the external field, we would actually be increasing the magnetic flux through the system. So what that would mean is as we increase the magnetic flux, we get further increases for free from the flowing current, and the flowing current would then just tend to build up and increase, and we'd be getting basically free energy out of the system for absolutely no investment. So we know then that Lenz's law tells us that the current can't be positive. It therefore had to come out negative, precisely as we had found through our detailed calculation tracking all of the various angles involved.